Welcome to the Deep Dive. Okay, grab your stack of sources. We've got articles, research, some really interesting personal notes here, and today we're diving deep into the history of the internet.
Yeah, it's quite a story.
Our mission, as always, is to pull out those key ideas, the pivotal moments, maybe some surprising characters that shaped this digital world we all live in now, straight from the material you've provided.
Sounds good.
Okay, let's unpack this.
So, the story really starts not even with connecting computers directly, but with a really radical idea about how data should actually travel.
Okay.
Forget the old way, like a phone call, needing that dedicated line the whole time.
Right, circuit switching.
Exactly. The breakthrough was thinking about breaking data into small, manageable chunks, little pieces.
These are the packets we hear about all the time. It seems, obvious now, doesn't it?
It does, yeah.
But your sources really underline that this wasn't some single eureka moment in one lab. Yeah. You had Dr. Donald Davies doing this at MPL in the UK and Paul Barron at Rand Corporation over in the US, basically coming up with the same core idea independently around the same time.
It's pretty amazing synchronicity, actually. Barron, way back in '62, he even had this great analogy. He called them message blocks, like hot potatoes that just needed to be passed along quickly.
Hot potatoes, I like that.
Yeah, in a sort of store and forward way. There was even earlier theoretical stuff. Leonard Kleinrock's thesis looked at information flow in big networks. So the seeds were definitely there academically in a few places.
So you've got this core concept, packets. How did that, theory start becoming something real, something tangible?
Well, that's where the visionaries come in. People who started thinking about linking computers together on a grand scale. Your sources really point to Dr. J.C.R. Licklider.
Ah, Licklider.
Yeah.
MIT, then BBN.
Right. He had this, honestly, incredibly ambitious idea he called the Intergalactic Network.
The Intergalactic Network. What a name. It really captures the scale, doesn't it?
It absolutely does. He was thinking thousands, eventually millions of computers all linked up.
And did they actually, try this out? Test if it was feasible?
Yeah, there was a really crucial experiment in 1965. MIT Lincoln Lab connected to System Development Corporation, SDC.
Okay.
And they tried using the traditional phone network approach, circuit switching.
Like making a phone call between computers.
Pretty much. And the conclusion was pretty stark. It just didn't work well. Computers talk in bursts.
Right. Sporadic data.
Exactly. Setting up a whole dedicated circuit for every little burst. Incredibly inefficient. It basically proved packet switching wasn't just a good idea, it was necessary.
Okay, so the need is clear. Packet switching is the way forward. And this is where the U.S. Department of Defense gets involved.
Precisely. They saw the potential, especially for robust, survivable communication. So the DoD adopted the packet switching concept in 1967.
And that led directly to ARPANET.
That's the one. The ARPANET project officially kicked off in 1968.
ARPANET, often called, the ancestor of the internet, and the first actual link. When did that happen?
That was 1969. They connected UCLA, University of California, Los Angeles, and the Stanford Research Institute, SRI.
And there's that great story, isn't there? But the very first message they tried to send.
Yeah.
A bit comical.
Oh, yeah. Perfect example of early tech. The plan was simple. Type login from UCLA to the SRI machine.
Simple enough.
But famously, the whole system crashed after just the first two letters went through.
No way.
Yep. So the very first message ever sent across the ARPANET was just low.
Low. That's it. Wow. A humble beginning for something so huge.
Couldn't be more humble.
Yeah.
But it grew fast. By December 69, they had 4 nodes.
4, okay.
And then it really took off. 40 sites by 1972. And just a quick note, ARPA itself got renamed DARPA that year. Defense Advanced Research Projects Agency.
Right, DARPA. Now, you mentioned the UK connection earlier. It's important we circle back to that because NPL's work wasn't just happening at the same time. It was actually influential, wasn't it?
Hugely influential. Your sources really stress this. Roger Scantlebury from NPL, he presented their work in the U.S. in 1967.
Okay.
And apparently the feeling was that NPL actually seemed more advanced at that specific moment.
Really? More advanced than the U.S. effort?
At that point, yeah. And Dr. Lawrence G. Roberts, who became the ARPANET program manager.
Right, a key figure.
He openly acknowledged NPL's impact. Critically, he adopted the term packet directly from Donald Davies' work at NPL.
So the name itself came from the UK work.
Yes. And maybe even more importantly, the speed. Roberts chose much higher speeds for the ARPANET links, 50 kilobits per second.
Which is fast then.
Very fast. And he did that specifically because NPL was already demonstrating those kinds of speeds. The initial US plan was apparently for much slower links, like 2.4 kilobits. That speed choice was absolutely vital for making the network actually usable early on.
That's a fascinating link. So ARPANET is being built, packet switching is the tech. But connecting all these different university research computers wasn't simple, I imagine. You couldn't just plug them all into one big box.
No, definitely not. They realized they needed separate, dedicated little computers just to handle the network communication tasks, to take the load off the main research machines, the hosts.
And these were the IMPs.
The interface message processors, exactly. IMPs.
Built by BBN Technologies.
That's right, BBN. Using Honeywell DDP-516 mini computers. And your source gives a nice shout out to the engineers at BBN who made it happen. The IMP guys.
The IMP guys.
Yeah, people like Frank Hart, Several Ornstein, Will Crowther, Dave Walden, Bob Kahn. They were writing this really complex assembly code to make the whole packet switching thing work in hardware.
So these IMPs, connected by phone lines, modems, that formed the core network, the backbone.
It was the subnet, yeah. The IMPs, the lines, the modems, that was the message switching network itself. And later they added something called TIPs. Terminal interface processors. They were clever because they let simpler terminals, just character-based displays and keyboards, connect directly to the network without needing a full host computer behind them. Made access easier.
Right, expanding access. And Licklider's intergalactic network vision, it wasn't just limited to the U.S., was it?
No, not for long. The first international connections came pretty early, actually, in 1973.
73, okay. Where to?
University College London, UCL, in England, and the Royal Radar Establishment over in Norway. They were the first nodes outside the U.S. to join the ARPANET.
And Peter T. Kirstein at UCL, your sources highlight him as a really key person here, sometimes called the father of the European Internet.
Yeah, he played a massive role, getting that first non-U.S. system connected and crucially demonstrating early on how different types of networks could potentially talk to each other. His work was fundamental for proving the whole internet working idea beyond just ARPANET itself.
Internet working.
Yeah.
Connecting networks together. And while the network's plumbing was being built, people were already starting to build things on it, right? Like email.
Oh, absolutely. Applications started appearing quickly. Your sources trace early mail commands way back to the mid-60s, even before ARPANET was fully live.
Pre-ARPANET email.
Well, the concept of sending messages between users on the same time-sharing system, yeah. That got ported to systems like Multics around 69. But email, as we kind of think of it, across the network, that really evolved on the ARPANET.
How did that happen?
The network working group, they started discussing mailbox protocols in early RFC's requests for comments.
RFCs, right. The documents that define internet standards.
Exactly. And here's a fantastic historical nugget for you. 1976. Queen Elizabeth II.
It's Queen.
The Queen herself sent an email announcing a new programming language facility was available via the ARPANET.
That's amazing. The Queen's sending email in 76.
And by that point, the familiar name-at-host format for email addresses, that was already the standard way to do it.
Wow. Some things really got established early. And they were even trying voice calls back then.
Yeah, experiments in the 70s, voice over the network.
Yeah.
The source mentions tests, including one using, believe it or not, a Mickey Mouse phone.
A Mickey Mouse phone. Seriously.
Apparently. Connected to equipment in that SRI mobile van we'll probably talk about later, decades before VoIP became common, they were already proving the concept.
Incredible. So, okay, the network's growing, emails flying, even voice experiments. But there must have been teething problems, reliability issues.
Oh, for sure. The very first protocol for communication between the main computers, the hosts, was called the 1822 protocol.
1822, okay.
It handled basic addressing, sending data, and it had an acknowledgement system, RFNM, ready for next message, which tried to guarantee delivery.
Tried, so it wasn't foolproof.
Not entirely, no.
Right.
The sources mentioned it wasn't completely reliable, but the bigger issues were more fundamental. It was designed mostly for just the ARPANET itself.
Right.
It couldn't easily address a computer that was on another network connected further down the line, and it didn't really provide robust error checking all the way from the sending computer to the receiving computer, just between the IMPs.
Which is a major problem if your goal is to build a network of networks, right? An internetwork.
Exactly. That limitation was critical. So to get more reliable delivery and to manage connections between specific applications running on different hosts, they developed NCP.
NCP Network Control Program.
Right. Stephen Crocker and the Network Working Group at UCLA, they spearheaded this.
And what did NCP do differently?
It provided reliable, flow-controlled connections between processes. So, like, your email application on one machine could talk reliably to the email application on another machine.
Okay. Application to application.
Yeah. And it's highlighted as an early example of protocol layering, separating the job of the network itself from the needs of the applications running on top. NCP rolled out around December 1970.
A big step. But even NCP had its limits, suggesting more work was needed.
It did. It still struggled with that problem of addressing hosts on networks further downstream. And that true end-to-end error control between the source and final destination host, that was still kind of missing.
So still not quite ready for a truly global internet.
Not quite. And those limitations were really pushing towards the next big evolution. Your sources even mentioned this incident in 1980. The whole ARPANET, about 213 hosts at the time, basically ground to a halt.
Froze up. Why?
Some kind of timestamp issue in the routing messages, apparently. It accidentally created a situation that looked a lot like a modern distributed denial of service, a DDoS attack, though unintentional. It just showed the fragility.
Okay, that sounds like the perfect storm leading to TCP/IP.
Exactly the right time. People realized they needed something more robust, more flexible, something designed from the ground up to handle potentially unreliable underlying networks, and crucially, to allow different kinds of networks to interconnect seamlessly.
And this is Vint Cerf and Bob Kahn's big moment.
Their seminal 1974 paper, it laid out the Transmission Control Protocol, TCP, explicitly designed to fix NCP's shortcomings, especially for internet working.
But wasn't TCP originally combined with IP? I thought they were separate.
They are now, but originally no. It was conceived as a single monolithic protocol. But as they developed and tested it, they had this key insight. It's actually more flexible, more powerful if you split the functions.
Split them how?
So in 1978, they divided it. You get the Internet Protocol, IP, whose only job really is addressing packets and forwarding them hop by hop towards their destination. Best effort, no guarantees.
Just get it moving in the right direction.
Pretty much. And then sitting on top of IP, you have the Transmission Control Protocol, TCP. That's the part that provides the reliability. It handles flow control, makes sure packets arrive in order, retransmits lost ones, does all the hard work between the end computers.
Okay. IP for addressing, TCP for reliability.
Yeah.
That makes sense. The TCP/IP suite.
That's it. And this layered approach, the separation, it became the foundation, and it caught on fast.
How fast?
By 1983, it wasn't just recommended, it was mandated. The Defense Communication Agency and DARPA made TCP/IP the official standard for the entire ARPANET. The Department of Defense adopted it too. Game over for NCP.
And Vint Cerf worked with others on this, right? Like Kirstein in London.
Yeah, the sources mentioned Cerf collaborated closely with Peter Kirstein and Bob Kahn on refining the design and actually getting TCP/IP implemented and tested across different networks.
And this split, TCP separate from IP, that's what really enabled connecting different types of networks.
Absolutely. If you have, say, ARPANET running TCP/IP and a satellite network running TCP/IP and maybe a packet radio network running TCP/IP, you just need a device in between that understands the IP addresses and knows how to forward the packets from one network to the next.
And those devices were the gateways?
Initially, yes. That was the term Vint Cerf and others used. As he notes, those gateways evolved and were later renamed to what we all call routers today.
Routers. Okay. Now, your sources mentioned the protocol wars. That sounds dramatic. It wasn't just a smooth transition to TCP/IP then.
Oh, far from it. The 80s were a battleground for networking standards. TCP/IP was gaining momentum, especially in the research and U.S. defense communities, but it had major rivals.
Like what?
Well, there was X.25. Very popular, especially in Europe, pushed by the big telecom companies. IBM had its own thing, S&A Systems Network Architecture. Digital Equipment Corporation, DEC, had DSNet. Everyone had their own proprietary way of doing things.
And the international standards bodies were involved too, ISO.
Right. The International Organization for Standardization developed the OSI model, Open Systems Interconnection, defined around 1980. It was this very comprehensive 7-layer model.
7 layers. I remember that from textbook.
Exactly. Theoretically very elegant, trying to standardize absolutely everything, but maybe too complex, too slow to implement fully.
So despite the grand OSI plan, TCP/IP won the war.
It did, pretty decisively. It became the de facto standard. Why?
Right.
Probably because it was more pragmatic, maybe easier to implement on existing and new technologies. It worked.
How do the layers compare, TCP/IP versus OSI?
TCP/IP is usually seen as having 4 or maybe 5 layers, depending on how you count. It sort of bundles together functions that OSI split into separate layers. Notably, OSI's session and presentation layers, layers 5 and 6, they never really had widely adopted counterparts in the TCP/IP world.
Interesting. So TCP/IP is the winner. We have routers. How did they actually start stitching these different networks together on a bigger scale?
Well, the need was immediate. Take the military side. ARPANET was connected to MILNET, the Unclassified Defense Network. They used gateways just to pass things like email between them, even before they were formally separated in 1983.
And internationally, beyond those first links to the UK and Norway.
Yeah, satellite played a big role. SatNet, the Atlantic Packet Satellite Network, used Intelsat satellites. That was a key link connecting the U.S. to Europe, sites like Goonhilly down in Cornwall in the UK, and also connecting to that SRI mobile van.
Ah, the van again. The mobile network node. That sounds so cool.
It really was cutting-edge stuff, and that van was part of some truly historic demonstrations. In 1976, it was involved in the first successful TCP/IP transmission between 2 different networks.
Which network?
The van's own packet radio network, PRNet, and the ARPANET, showing TCP/IP could bridge different underlying technologies.
Okay, 2 networks. But then they went further.
Even better, 1977. The first demo across 3 distinct networks, this is classic, data went from the SRI van, parked in Menlo Park, California, to the University of Southern California, USC. But, and here's the amazing part, the path went via London.
What, California to California via London?
Exactly. It went from the van on the packet radio network, then hopped onto SatNet, the satellite link, across the Atlantic to London.
Wow.
Then from London, it came back across the ARPANET to USC and LA. Packet radio, satellite, ARPANET, 3 different networks stitched together by TCP/IP and those early gateways. Concrete proof that the internetworking concept worked on a global scale.
That's incredible. A round trip across the world just to prove a point. It really shows the power of the idea.
Absolutely. And Robert Kahn, one of the TCP/IP inventors, specifically mentioned how crucial the invention of those gateways, soon to be routers, was to making this all possible.
Okay, so routing between networks is solved, conceptually at least. But as more computers joined, just keeping track of where everything was must have become a nightmare. IP addresses are just numbers, right? How did people manage?
Yeah. By 1983, it was a massive headache. Your sources highlight this. They were literally managing all the known computer names and their IP addresses in a single text file. Hosts.txt.
One file for the whole network.
One central file maintained at SRI's Network Information Center, the NIC. You had to download updates. It just couldn't scale. Imagine doing that today with billions of devices. Maybe it worked for a few hundred, maybe 1,000 hosts, but beyond that, no way.
So they needed an automated distributed system.
Desperately. And this is where the domain name system, DNS, comes in.
DNS?
Yeah.
Translating names like google.com into IP addresses.
Exactly. A working group, including, again, key people like John Postel, plus Paul Mockapetris and Craig Partridge, they came up with this idea of a distributed database. Instead of one central file, the information is spread out across many servers.
More scalable.
Infinitely. This concept became DNS, based on early RFCs like 819 and 882, and the very first DNS server to go online around 1983-84 was built by Paul Mockapetris. It even had a name, Jeeves.
Jeeves. Like the butler.
Apparently so. DNS was formally defined in RFC 920 in 1984 and became operational. It completely changed how users and applications found things online. It could use memorable names instead of raw numbers.
And John Postel's name keeps popping up in these foundational moments. Address management, numbers.
He was absolutely central to coordinating all this early on. He ran the Internet Assigned Numbers Authority, INA, basically overseeing IP addresses, domain names, protocol numbers. Your sources even mention RFC 2468, written in his memory, which starts a long time ago in a network far, far away. A nice nod to his huge contribution.
That's great. So DNS solves the naming. But how did the routers themselves share information about the best paths between all these different networks that were now springing up?
Good question. Initially, between the core gateways of the early internet work, they used fairly simple protocols. GGP was one, gateway to gateway protocol.
How did GGP work?
It used what's called a distance vector algorithm. Basically, each gateway told its neighbors how many hops, how many other gateways it took to reach certain networks. You'd just pick the path with the fewest hops. Simple, but limited.
And they started thinking about organizing the internet into bigger chunks.
Yes, the concept of autonomous systems, or ACs, emerged. An AS is basically a network or a set of networks all under a single administrative control, like a university campus network or an early ISP.
Okay.
And to exchange routing information between these different ACEs, they developed EGP, the Exterior Gateway Protocol, defined in RFC 904.
EGP. So that let different organizations share which networks they could reach?
It did, but EGP had its own limitations. It sort of assumed the internet had a tree-like structure with no loops, which quickly became unrealistic. RFC 1009 in 1987 helped formalize these ideas about LANs, WANs, and autonomous systems.
Right. Okay, we focused a lot on the big picture, the ARPANET, connecting universities and networks. But what was happening inside organizations? Within a building or a campus?
Well, that's where local area networks, LANs, really took off, and you have to talk about Xerox PARC.
Palo Alto Research Center.
Yeah.
Famous for the graphical interface, the mouse.
Exactly. Hugely innovative place in the 70s. They developed the Alto computer, GUIs, all that. And they also needed a way to connect their own computers together locally.
So they built their own LAN.
They did, around 1973-74, and a key figure there was Robert Metcalfe. He'd been inspired by Aleranet, this experimental radio network in Hawaii.
Right, using radio waves.
Yeah. Metcalfe proposed doing something similar but using coaxial cable instead of radio. He wrote a memo in 1973 proposing the Ether network.
The Ether network. There's that name again? Based on the idea of the luminiferous ether.
That was the inspiration, yeah. His core technical idea was CS-MAC-CD.
Okay, break that down. CS-MAC-CD.
Carrier sense, multiple access with collision detection. It's like a polite conversation at a dinner party.
Okay.
Carrier sense. You listen to see if the ether is busy before you talk. Multiple access. Anyone can try to talk when it's free. Collision detection. If two people start talking at exactly the same time, a collision, they both detect it, stop immediately.
And then wait a bit before trying again.
Exactly. They wait a random amount of time. That's the truncated exponential back-off part so they don't just collide again immediately. It's a clever way to share a single cable.
It sounds complex but elegant. Xerox patented this.
They did in 1975. And the first commercial version, Ethernet version 1, came out in 1980.
How fast was it?
10 megabits per second, which was blazing fast for a local network back then. It used those 48-bit MAD addresses that are still used today.
And this became a standard.
Yes. 3 major companies, Digital, DEC, Intel, and Xerox, collaborated on a standard, often called the DIC standard, that heavily influenced the formal IE 802 project, which was working on LAN standards. The result was IE 802.3 CSMAD, formally approved around 82, published 85. That was Ethernet.
And your sources mentioned there were competitors, right? Ethernet wasn't the only LAN game in town.
No, definitely not. IBM was heavily pushing Token Ring. There was ArcNet, the Cambridge Ring in the UK, ChaosNet at MIT. Quite a few contenders. But Ethernet ultimately won out for most uses.
What did early Ethernet look like physically?
Very different from the cables we plug in now. The first standard was 10-base-5, often called ThickNet. It used this thick, stiff, yellow coaxial cable, usually run in ceilings.
ThickNet, okay.
And you connected computers using these things called vampire taps. You literally had to drill a hole into the cable to tap into it. It was kind of cumbersome.
The vampire taps. That sounds invasive. Okay, back to universities. Stanford was key in ARPANET, but they also played a big role in routing hardware, didn't they?
Yeah.
Connected to Cisco.
Absolutely. Stanford's own campus network, SUNet, was migrating to TCP/IP in the early 80s, and they needed a way to connect all their different types of computers, DEC, IBM, Xerox Altos, you name it.
They needed a translator box.
Essentially, yes, a multi-protocol router. And in 1981, they built one, nicknamed the Blue Box.
The Blue Box, who built it?
It was a team effort. Leonard Bosack managed the project. Andy Bechtolsheim did a lot of the hardware design, and crucially, William Yeager wrote the network operating system in C. Its whole purpose was to let all these disparate systems on campus talk to each other using different protocols.
And this Blue Box became the basis for Cisco.
Directly. Leonard Bosack and his partner Sandy Lerner, who also worked at Stanford, saw the commercial potential. They left Stanford and founded Cisco Systems, originally lowercase Cisco, in late 1984.
Based on that Blue Box tech and Yeager software.
Yes. Now, there was a bit of a dispute with Stanford about the intellectual property.
Ah, the classic startup story.
Pretty much. It was eventually resolved with Stanford licensing the technology to Cisco.
And Cisco's early routers, like the AGS, they took off quickly. What was their edge?
The software, really. Yeager's network operating system, which became Cisco iOS, its huge advantage was that multi-protocol support right from the start. It could handle TCP/IP, sure, but also DCNet, XNS from Xerox, AppleTalk, X.25, IBM protocols. Whatever customers had, Cisco could probably route it. That was massive. And it supported dynamic routing protocols early on, too.
Okay, so routers are getting sophisticated. But as the internet itself kept growing like crazy in the late 80s, that EGP protocol for routing between autonomous systems, that started creaking, right?
Badly. EGP just couldn't scale. It couldn't handle the increasingly complex mesh-like structure of the growing internet. It assumed a simpler tree-like topology. They needed something much more robust.
And this leads to another great origin story.
One of the best. The 3 ketchup-stained napkins story.
I love this one. Tell it.
Okay, so the story goes, it's 1989 at an IETF meeting, Internet Engineering Task Force. Kirk Lougheed from Cisco and Yakov Rector from IBM are sitting down, probably having lunch or coffee, trying to hash out ideas for a replacement for EGP.
Right.
And they literally sketched out the initial concepts for a new protocol on 3 napkins, which, legend has it, were stained with ketchup.
3 ketchup-stained napkins. You can't make this stuff up.
Apparently not. And for a while, the protocol was informally called the 3-napkin protocol, but it became BGP.
BGP, Border Gateway Protocol.
Exactly. The first version, BGP1, was published in RFC 1105 in 1989. It was deployed pretty quickly, but it evolved. BGP2 added path attributes, BGP3 improved scaling, but the really big one was BGP4.
BGP4. Why was that so important?
Published in RFC 1654 in 1994. Its key innovation was support for CIDR.
CIDR, classless interdomain routing.
Right. Before CIDR, IP addresses were strictly divided into classes A, B, C, which was incredibly wasteful. CIDR allowed network administrators to aggregate blocks of IP addresses into larger chunks and advertise them much more efficiently. It saved the internet's routing tables from exploding.
So CIDR made BGP scalable for the massive growth to come.
Absolutely essential. And BGP4, with CIDR, is fundamentally still the protocol that holds the global internet together today. Yakov Rector himself has confirmed the napkin story, by the way.
That's fantastic. Okay, so by the early 90s, TCP/IP is standard, DNS is working, BGP is emerging for routing. What happened to the original network, ARPANET?
Its job was done, essentially. The ARPANET was officially decommissioned in 1990.
The end of an era.
It really was. By that point, the main backbone carrying U.S. internet traffic had shifted to NSFNet.
The National Science Foundation Network.
Right. It started by connecting supercomputing centers, building on an earlier network called CSNet.
And NSFNet got faster.
Significantly. They upgraded the links. T1 speed, which is 1.5 megabits per second in 89. Then T3, which is 45 megabits by 1991. That was serious bandwidth back then.
And crucially, the NSF encouraged others to connect.
Yes, that was key. They promoted the idea of regional networks and encouraged local organizations to provide connections. This really spurred the creation of the first commercial internet service providers, ISPs, around 1991.
The birth of the ISP industry.
Yeah.
And the rules about commercial traffic changed too. That must have been huge.
Absolutely pivotal. Originally, NSFNet had an acceptable use policy that basically prohibited commercial traffic. But in 1991, the NSF changed its policy. They allowed commercial use on ANSNet, which was the upgraded NSFNet backbone run by a nonprofit formed by IBM, MCI, and Merit.
So the door opened for business on the internet.
Wide open. That policy change transformed the internet from primarily a research and academic network into the commercial platform we know today.
And this led to ISPs needing ways to connect directly to each other.
Exactly. If you were a commercial ISP, you didn't necessarily want to pay to send traffic over the NSF backbone if you could just hand it off directly to another ISP your customer needed to reach. This led to the formation of CIX.
CIX, Commercial Internet Exchange.
Formed in 91 by some of the earliest big commercial ISPs, PSIN, UNet, SurfNet. Their goal was to create a neutral place where they could connect their networks together and exchange traffic directly, peering, without usage fees.
So CIX was basically the first IXP Internet Exchange point.
Essentially, yes. Your sources point that out. It was the model for the hundreds of IXPs that exist around the world today, which are critical interconnect points.
And BGP had to evolve to handle this new world of commercial peering, especially as NSFNet faded away.
Right. BGP2 and BGP3 were developed partly to handle the more complex peering relationships and the transition away from relying on a single government-funded backbone. It enabled the multi-provider, commercially driven internet structure we have now.
Okay, the infrastructure is getting there. It's becoming commercial. But for an ordinary person getting online in the early 90s, how did you actually find anything? It sounds like it's still pretty arcane.
Oh, it really was. Compared to today, night and day. Mostly, you were looking for files on FTP servers.
File Transfer Protocol.
Right. And You generally had to know the exact address of the FTP server you wanted. People shared lists of interesting sites. There were Usenet news groups discussing them, even actual printed books listing resources.
A printed book of websites. Or FTP sites.
FTP sites mostly, yeah. It was incredibly manual.
So, early attempts to organize this information.
There were a few. Archie is often cited as the first internet search engine.
Archie. Like the comics.
Named after archive, apparently. It wasn't searching web pages because they didn't really exist yet in the way we think of them. It was basically a tool that periodically scanned the listings of public FTP servers and built an index of file names. You could then query Archie to find which server had a specific file.
Okay, finding files. What else?
There was Gopher, defined in RFC 1436. Gopher presented information in hierarchical menus, like navigating through folders on your computer. You'd connect to a Gopher server, see a menu, pick an item, get another menu, and so on. It was structured, text-based, quite popular for a while.
Gopher, I remember that name.
And Waze Wide Area Information System. That was more ambitious. It used a library cataloging protocol, Z39.50, to let you search the content of documents across different servers.
So Archie for file names, Gopher for menus, Waze for content searching. Important steps.
Definitely important precursors, but they were all about to be overshadowed by something much, much bigger.
The World Wide Web.
The absolute game changer. And this brings us to Tim Berners-Lee at CERN, the European Organization for Nuclear Research.
Right, his 1989 proposal.
Information management. The proposal. It laid out the vision. He saw the need for a way to link information together easily across different computers and different formats. His solution combined hypertext clickable links with the internet.
And crucially, he didn't just invent it, he gave it away.
That was key. In 1993, he released the software for the first web browser, which he also called World Wide Web, later renamed Nexus to avoid confusion, and the first web server. And critically, CERN made the underlying code libraries freely available. No royalties, no patents holding it back.
What were the core technologies he created?
3 main things. HTML, hypertext markup language, for creating the documents with text, links, images. URLs, uniform resource locators, for giving every resource a unique address. And HTTP, hypertext transfer protocol, for fetching those resources across the network.
HTML, URL, HTTP, the foundations. And graphical browsers made it usable for non-techies.
Massively important. There was an early one called Viola www in 92, but the one that really broke through was Mosaic.
Mosaic from NCSA.
National Center for Supercomputing Applications, yeah. Released in 1993, Mosaic was revolutionary for a couple reasons. First, it was the first browser to display images in line with the text on the page, not in a separate window. Made pages look much more engaging.
Right, integrated images.
And second, they made versions for Unix, Mac, and Windows. That cross-platform availability was huge. Suddenly, lots of people could easily access the web graphically.
And the lead developer for Mosaic was Mark Andreessen.
That's right. He left NCSA shortly after Mosaic's release and co-founded Netscape Communications.
Netscape. Their browser, Netscape Navigator, came out in 1994.
And it just took off like a rocket. It was faster, had more features than Mosaic. For a while in the mid-90s, Netscape Navigator was the web for most people. It drove adoption incredibly quickly.
It's funny how fast things changed. Your sources have that quote from Bill Gates around that time.
Oh, yeah, the 1994 quote. Gates saying something like, "I see little commercial potential for the internet for the next 10 years.
Oops. A rare miss for him.
A big one. Shows how even brilliant people can underestimate disruptive technology.
And Microsoft obviously changed its tune quickly, which led to the browser wars.
Oh, yes. Microsoft realized they'd missed the boat and scrambled to catch up. They developed Internet Explorer and, crucially, bundled it for free with Windows. That bundling was a major factor in Netscape's eventual decline and led to significant antitrust lawsuits against Microsoft, arguing they used their Windows monopoly unfairly.
A whole saga in itself. And the growth of the web itself during this time, the numbers are just mind-boggling.
Absolutely staggering. Your source data shows it maybe 10 websites total in 1992, 130 in 93. It hits 1 million by 1997, 17 million by the year 2000.
Yeah.
And today, well over 1.8 billion. Just explosive growth.
And for most ordinary people jumping onto this exploding web from home in the 90s, how were they connecting?
The soundtrack of a generation, dial-up modems.
That screeching, buzzing sound.
Exactly. That was the standard way for home users to get online throughout the 90s. Modem, of course, short for modulate demodulate.
Modulate demodulate, what does that mean?
It means converting the computer's digital data into analog sound signals that could travel over the regular phone line, that's modulation. And then the modem at the other end converts the sounds back into digital data demodulation.
So it's translating between digital and analog sound.
Precisely. Early ones, acoustic couplers where you literally jammed the phone handset into rubber cups, were painfully slow, but standalone modems got much faster through the 90s. 14.4K, 28.8K, eventually hitting the peak of 56K, following standards from the ITU TV series.
And that dial-up sound was the sequence of modems negotiating the connection.
Yep, the handshaking process. Every step had a distinct sound. And ISPs, the companies you paid for access, they had buildings with rooms just full of racks upon racks of modems and chassis, handling thousands of incoming calls simultaneously. Companies like Hayes were big names in modem.
Racks of modems. Wow. Okay,
Yeah.
So the web is booming. People are dialing in. But finding specific information on the web needed better tools than Archie or Gopher, right?
For sure. As the number of web pages exploded, finding relevant information became the next big challenge. We saw the first wave of web search engines emerge.
Beyond just directories like Yahoo.
Yeah, Yahoo started as a hand-curated directory which couldn't scale. True search engines appeared. WebCrawler in 1994, notable because it was the first one to index the full text of web pages, not just titles or headers.
Searching the actual content.
Right. Lycos also launched in 94. Alta Vista came along in 95 from Digital Equipment Corporation. It was very powerful for its time, had a huge index. These were the big names before Google.
And people weren't just consuming information, they started creating their own little corners of the web.
Absolutely. This was the era of the personal homepage. Early free web hosting services popped up. Tripod started in 94, Angel Fire in 96, and maybe the most famous, GeoCities.
GeoCities. With the neighborhood.
Exactly. Launched in 94, you could build your free website and place it in a themed neighborhood like Hollywood or Area 51. It was a huge part of early web culture, letting anyone put their mark online. Lots of blinking text and animated GIFs.
Oh, the blinking text. Good times. Which brings us inevitably to the search engine that changed everything. Google.
Founded in 1998, came out of Stanford, PhD project by Larry Page and Sergey Brin. Scott Hassan also did a lot of the early coding.
And the breakthrough wasn't just indexing more pages, it was how they ranked them, right? PageRank.
That was the secret sauce, PageRank. Instead of just counting how many times a keyword appeared on a page, Google's algorithm looked at the links pointing to a page from other pages.
Treating links like votes of confidence.
Exactly. A link from an important page counted more than a link from an obscure one. It was a fundamentally better way to judge a page's authority and relevance. It produced much, much better search results, and that's why they took over so quickly.
Makes sense. Now, while the web and search were grabbing headlines, the underlying network technology, especially in LANs, didn't stand still either.
Not at all. That thick coaxial Ethernet cable 10BASE-5 was quickly replaced. The dominant standard became 10BASE-T.
10BASE-T, what was different?
It used much cheaper, more flexible, unshielded twisted pair cable UTP. Basically the same kind of cable used for telephones, but with specific wiring standards. And crucially, it used star topology.
Star topology, meaning?
All devices connect individually to a central point, a hub, instead of sharing one long bus cable. Much easier to manage and troubleshoot. This was standardized in IEEE 802.3i in 1990.
And hubs were the central connecting devices.
Initially, yes. Hubs were simple devices that just repeated any signal they received on one port out to all other ports. Companies like Synoptics with their LatticeNet system, 3Com, Cabletron, they were huge in the 10BASE hub market. This shift also drove the adoption of structured cabling systems within buildings.
So hubs connected everything. But the router market connecting different networks, that was still competitive. Cisco wasn't alone?
Cisco was definitely becoming the dominant player, but they had serious competition, especially in the late 80s and early 90s. A company called Wellfleet Communications was a major rival, making powerful routers. There were others, too.
But then came another big invention that changed LANs fundamentally, moving beyond hubs.
Yes, the Ethernet switch, invented by a company called Kalpana in 1990.
How is a switch different from a hub?
A hub shares the bandwidth. If you have a 10 Mbps hub, everyone connected shares that 10 Mbps. A switch is much smarter. It learns which device is connected to which port, and it forwards traffic only to the specific port where the destination device is.
So it creates separate paths. Less congestion.
Exactly. Each port on a switch effectively gets its own dedicated bandwidth, reducing collisions dramatically and boosting performance. It was a massive improvement over hubs.
And Cisco saw the potential there.
They sure did. Cisco acquired Kalpana in 1994. It was one of their early major acquisitions, setting a pattern for how they'd grow. They also got technology like Ether Channel from Kalpana, which lets you bundle multiple links together for more bandwidth, the basis for today's link aggregation groups. LEGs.
So switches took over from hubs, and LAN speeds just kept climbing.
Relentlessly. After 10 millips, Ethernet came 100 millips, fast Ethernet, standardized around 1995. Then gigabit Ethernet, 1000 Mbps, around 1999. Then 10 gigabit Ethernet in the early 2000s, first over fiber optic cable, later over advanced twisted pair copper.
And the routing protocols used inside networks evolved too.
Yeah, within enterprises, people moved away from older protocols like RIP, which was based on hop count, towards more sophisticated link state protocols like OSPF, Open Shortest Path First. Cisco also pushed their own advanced protocol, EIGRP. These gave much faster convergence and better path selection.
Your sources also mentioned ATM, asynchronous transfer mode. Was that a big deal?
For a while in the late 90s and early 2000s, ATM was hyped as the future high-speed technology for both LANs and WANs. It used small, fixed-size cells instead of variable-length packets. Some core networks used it, but ultimately, Ethernet kept getting faster and cheaper, and TCP/IP proved incredibly adaptable. So Ethernet and IP running over optical networks largely won out.
Speaking of optical networks, how did the core internet links, the big backbone pipes, keep up with all this exploding traffic from LANs and the web?
Primarily through optical fiber technology, specifically SONET in North America and SDH internationally. Synchronous optical networking, SPIGs ramped up dramatically.
Like what kind of speed?
We saw OC48 links running at 2.4 gigabits per second, then OC192 at nearly 10 GBps becoming common in the backbone. And service providers deployed MPLS multi-protocol label switching on top of these links.
MPLS, what did that do?
MPLS is a technique service providers use to forward traffic more efficiently across their core networks. It adds labels to packets at the edge of the network, and the core routers just switch based on those simple labels, which is faster than doing full IP lookups at every hop. It helps scale the backbones.
And speeds went even higher.
Oh, yeah. OC768, running at 40 gigabits per second, became available around 2006. Your sources mention AT&T deploying it on their backbone in 2008, including on transatlantic cables like TET-T14.
40 gigabits across the Atlantic in 2008. And today?
Today, the backbone relies on hundreds, over 600 submarine fiber optic cables circling the globe. And they use a technology called DWDM.
DWDM.
Dense Wave Division Multiplexing. It basically allows them to send many different data streams down a single strand of fiber simultaneously using different wavelengths or colors of light. It multiplies the capacity of each fiber enormously. And those IXPs we mentioned, like LIMNEX and London, are more crucial than ever for interconnecting all these networks efficiently.
It's an incredibly complex global machine. How do analysts or network engineers even think about its structure today? Is there a model?
Your sources describe the common way to visualize it is as a hierarchy, usually 3 tiers of service providers.
Tier 1, 2, and 3.
Exactly. Tier 1 providers are the huge global backbone networks. Think companies like Lumen, Cogent, or Reliant, maybe big telecoms like AT&T or Verizon's backbone division. They have global reach, and crucially, they interconnect with each other without paying. That's called settlement-free peering. They exchange traffic freely because they're roughly equal.
Okay, Tier 1s peer with each other. What about Tier 2?
Tier 2 providers are usually large regional or national networks. They might peer with some other Tier 2s or Tier 1s, but they generally also have to buy connectivity called transit from one or more Tier 1 providers to get access to the entire internet.
So they pay Tier 1s for global reach. And Tier 3?
Tier 3 providers are typically your local or smaller regional ISPs. The company that provides internet to your home or business. They almost always buy transit from Tier 2 or Tier 1 providers to connect their customers upstream to the rest of the internet.
So when I connect from home, my traffic goes through my Tier 3 ISP, up to their Tier 2 or Tier 1 provider, and then across the Tier 1 backbones if necessary.
That's generally how it works, yeah. And you can actually see this path using tools like Traceroute or graphical versions like Visual Route. They show you the sequence of routers, often across different providers and peers, that your data packets travel through to reach a destination. There have even been cool visualization projects like the Internet Mapping Project from Bell Labs years ago, trying to map this complex structure.
Fascinating. It's clear this whole story is packed with technical breakthroughs, but your sources also touch on the cultural side, the concepts that emerged alongside the technology.
Absolutely. It wasn't just about bits and bytes. You have terms like Eternal September.
Eternal September, what's that?
It refers to September 1993, when AOL started offering Usenet access to its huge user base. Before that, Usenet access grew more gradually, often with university students joining each September. But the sudden influx of AOL users, many unfamiliar with existing Usenet etiquette, felt like a never-ending wave of newcomers disrupting the existing culture. It became a symbol of how mainstream growth changed early online communities.
The clash of cultures online. And there were online communities before the web really took off.
Oh, yes. The Whole Earth Electronic Link started way back in 1985. It was a very influential early online community, fostering deep discussions long before social media giants existed. Shows the desire for online connection has been there a long time.
And the word we use all the time, cyberspace. Where did that come from?
Not from a tech paper. It was coined by the science fiction author William Gibson in his 1984 novel Neuromancer.
Neuromancer. A classic.
He described it as a consensual hallucination experienced daily by billions, a shared virtual space made of data. That fictional concept powerfully shaped how people imagined and talked about this new digital realm that was being built.
Fiction influencing reality. It's amazing how these technical, cultural, and even fictional threads weave together. And speaking of personal experience, your sources include some really insightful notes from John A. Clark, who was apparently right in the thick of it for much of this history.
Yeah, his personal perspective is fantastic. It grounds the timeline. He talks about actually installing TCP/IP systems at the London Stock Exchange back in 1986.
1986. That's only 3 years after ARPANET mandated it. Very early adopter.
Very early in the commercial world, yes. He was also teaching engineers about Ethernet and TCP/IP back then, as these technologies were just starting to become mainstream in business.
And he saw the web happen in real time, too.
He wrote his first ever personal homepage in raw HTML back in 1994. He notes there were only maybe 3,000 websites in the entire world at that point.
Only 3,000. Incredible.
And get this, he mentions writing his resignation letter from one job on an internal company webpage he created.
Quitting via HTML, that's definitely a sign of the times.
Isn't it? He also recalls this specific moment in 1995 that really struck him. He was in the U.S. and he pulled up a web page that he knew was being hosted on a server back in his office in England.
Just a normal thing now.
Completely normal now. But for him, back then, seeing that page appear instantly from across the Atlantic, it was this profound moment. It just clicked. The internet was truly global, truly connecting everything.
And he worked through what he calls the golden period of networking.
Yeah, working for major networking vendors during that explosive growth phase. He saw speeds jump from kilobits to megabits to gigabits. He was implementing all these new protocols we've talked about, OSPF, MPLS, setting up complex BGP peering for big customers. He was even a design authority for massive projects like the networking infrastructure for the HSBC headquarters building in London.
Wow. Hands-on experience at the highest level.
And he makes a final note that just writing this history page itself, the source material we're using, was a long-term project for him. Started around 1997, finally finished in 2025. That really speaks to the depth of the history and his long involvement in it.
That personal viewpoint really brings it home. It wasn't just abstract technology, it was people building, deploying, and experiencing this incredible transformation over decades.
It underscores the immense human effort and the cumulative nature of all this innovation.
Okay, here's where it gets really interesting. So, what does this all mean? We've traced this incredible path, haven't we? From, these separate ideas about packets.
Through Licklider's intergalactic dream.
The practical reality of ARPANET.
The battles of the protocol wars settling on TCP/IP.
The invention of routers. Cisco rising.
Ethernet taking over lands.
Then boom, the World Wide Web changes everything.
And this relentless scaling, connecting, building the global network we rely on today, it's an amazing arc.
It really is. A story of, layers of innovation, fierce debates, breakthroughs, and just connecting things up.
Protocol by protocol, cable by cable.
So thinking about this whole journey, from that first 2-letter message, low, crashing the system.
Right.
To today.
Yeah.
With billions online and over 1 billion websites.
Yeah.
It really makes you think, doesn't it? Consider this. How much are those very early decisions, those foundational choices made decades ago, still shaping our experience today?
What do you mean exactly?
Well, think about the fundamental choice of packet switching versus circuits. The specific layered design of TCP/IP. The way BGP was designed to route between autonomous systems. Even the compromises made, maybe, during those protocol wars. How much is that original DNA still influencing the internet we have now?
Ah, I see. Like the legacy of those early designs.
Exactly. How do those deep-down architectural choices continue to shape the challenges we grapple with today? Things like network security, user privacy, net neutrality debates, even the raw speed and inherent structure of the network itself. It feels like those early decisions are still echoing, you know?
That's a really interesting point, the path dependency of it all.
Yeah. Something to think about definitely as you click and scroll through this vast, constantly changing digital world that was built, sometimes intentionally, sometimes almost accidentally, layer upon layer over all these years.